Okay, so we need to just refresh on, okay, what is entropy? And then how do we actually calculate a value for it? Then Gibbs free energy, what is that related to? I keep saying that's like the granddaddy Supreme Court final say on if something is thermodynamically favored or not. All right, so if we could, phenomenal students, oh, I know what we're going to next. Okay, so today, our goal is to judge if it is thermodynamically favored or not, but we may use the term spontaneous. I found the actual literature that said the College Board is favoring this terminology because of how many students confuse the term spontaneous with everyday language. But we are bright, amazing students that realize spontaneous in chemistry doesn't mean on a whim or very fast. It just means happens without us doing anything, inputting energy. So the creation of an Oscar statue does not happen without the input of work, non-thermodynamically favored. Okay, we talked about, okay, how do we find the value of enthalpy, the value of the heat that is required or released by a chemical reaction, and we're usually looking at the change. Okay, what do we get out, or what do we have to invest? And we said that there's, in general, 3 ways. We went over these last week. Calorimetry, using Hess's law. We could also, if we know the enthalpy of the reaction, use that as kind of a conversion factor. So kind of like the stoic given the enthalpy of the reaction, and usually standard state, or enthalpies of formation. We can also use bond energies, and we'll review that. Okay. Well, we talked about how do we judge the sign of enthalpy, right? What does it mean if it's a positive or a negative change in enthalpy for the reaction of the process? And what would be thermodynamically favored? All right, entropy. So, Anna, if I asked you to tell us what is entropy in one word, what word are you most comfortable with? Dispersion. Oh, 2 words. Positional probability. Another one is the number of microstates. So, dispersion, I like that a lot. And so, if it's positive, then that process is increasing the dispersion. Negative, it's decreasing. And strangely enough, thermodynamically favored is increasing. And we talked about examples in our world that show that. So this was just another, and it's the same thing as positional probability. We could just call it, instead of number of positions, number of microstates. So, taking seats in an auditorium, the number of arrangements that are possible, we could call microstates. Okay. We looked at questions that were similar to this on Thursday. So, what if you were asked, okay, so everybody, like, hear my voice, transform it from, the peanuts to here. All right. Which of these has the greatest increase in entropy? Can we see okay? God bless you. Okay, so Porter, when we're looking for an increase in entropy, what would we be looking for if we're given chemical reactions?
Increase in the amount of moles, or it changes the gas,
Ah,
liquid or solid.
okay, could it be just straight out number of moles? Does the phase matter? Or is it just strictly number of moles? It does. So we have to look at a couple things. Number one would be, okay, is there any of these where I make gas where there's no gas? Especially if we start in the solid phase. The solid phase has the least amount of dispersion. So if given a container, a solid, we know that the particle attraction is limiting the movement. It does not expand to fill the entire container, where a gas, it would. So if we're creating gas where we did not, or if we had gas, just more moles of gas. So I would look at the number of moles where your phases are tied. So that first situation, gas, 2 moles, 2 moles. Nah, no change, no increase. I mean, we could look at, well, what about the size of the molecule? But let's look at and see if there's something else. Well, in B, yikes, we have 4 moles of gas moving to 2. That is decreasing. Then in C, we have solvated ions. Oh my gosh, forming a crystalline solid, definitely decreasing. In D, 3 moles to 1 mole. But in E, we have solid, and we're making solid, but we're producing gas. So it would be E all day long. Is that okay? Yeah, exactly. I didn't know what we needed. Thank you. Yeah. And so whenever we have the solid state, that would be the least dispersion. So as far as entropy, solid, liquid, gas, this would have the lowest entropy than. And then of course, when we're talking about, you know, a solute aqueous, you know, that would fall in this category as well. Okay, Sarah? Okay. So thank you for having me go back to that. Okay. So the next thing that I'd like, Maxwell Boltzmann distribution. Not that we ever have to remember that this is what it's called. So what if we were asked which sample has a higher entropy and justify? Jackson. Because so
The particles are moving faster, so like there'd be
so we know that as we go from, okay, so that had A and then B. Oh, crud. A was higher. Sorry, that was very lame. Ignore that. Okay. This is number of particles, and then this was speed. We need to remind ourselves, okay, what influences the speed of gas? It is molar mass and temperature. So I would look at the average. So temperature A or sample A has an average there. B, it is either that it has a smaller molar mass or a greater temperature, which I would venture to say greater temperature. And we can just say, okay, the greater the temperature, the greater the kinetic energy. We know temperature and kinetic energy are directly proportional. The greater the kinetic energy, the greater the dispersion. We are okay to just make that association. Even if they're in the solid state, you're going to have the most wiggling. Oh, but I was also going to say, also, the greater speed, there's a greater variety of different actual values, right? That's where the Maxwell-Boltzmann distribution comes from, that sample B has molecules that are this speed all the way over to the edge. Yeah? Where A doesn't have the variety that B does. we have to understand that A would extend a little further too. Yeah, and so they're representing, symbolizing a greater number of microstates. Okay, Maya, do we want to make water, take water apart? You choose, composition or decomposition. Okay, so can we, well, actually, so this is the next thing I want to take a look at. Oh, yeah, that next, sorry. Okay, how do we employ this equation? So if you could, in the very back of your packet, the very back of your packet. Okay, I'm giving us a really nice and easy reaction to analyze. Okay. Oh, Maya, I need you to repeat. How embarrassingly. You said make water. Yes. Okay. So we are making water. Oh, and even go this far. Are we making it in the solid state or the liquid state, gaseous state? Ah. Okay. Then we will make it, we know, from H2 and O2. Oh, do we want to make it from? Yeah, let's do it. Let's just do this. And we'll need a 2 and of course a 2 to balance. Now, I know that Abby is thinking, oh, Mrs. Gerhardt, I thought for a second you were writing the enthalpy of formation until you put that 2 in front of the water. Remember, enthalpy of formation, we're making 1 mole of substance from its elements in the reference form. Okay, so what if I wanted to know the entropy of this? Well, first off, Jackson, what would you anticipate the sign is? Positive or negative? Because?
You have 3 moles of that.
Perfect. Perfect. And so we're thinking this is going to decrease our entropy. So it is not experimentally favored thermodynamically as far as entropy goes. But let's calculate the value. So what we can do is sum the absolute entropy of the products, but we must take into account the moles of each minus the summation of moles of reactant. Okay, so Alexa, could you in the table find the absolute entropy of H2 gas? Leah, could you find O2 gas for us? And Rachel, do you mind finding H2O gas, the absolute entropy? And so remember, these are quote unquote alphabetical. So if we want to go to hydrogen, then oxygen. Whenever you have it, say it loud. Perfect. What are the units? Wonderful. All right, now take a look. I know that this will not cause us to make errors. Look at the units on absolute entropy, joule per Kelvin mole. But enthalpy of formation and Gibbs free energy of formation are in kilojoules. So we need to be careful if we're ever using these values together, which of course we will. Usually, because of just the numbers we'll be given, kilojoules are preferred. And so often we'll just have to convert our entropy values to kilojoules. Okay, so H2 gas is 131. Anybody have the oxygen and the water? Perfect. And water in the gaseous? Thank you. Thank you. And remember, oh my gosh. Kelvin mole. These values are calculated using the third law of thermodynamics, that at 0 Kelvin, all of these values will be 0. So of course, we're at standard state. These will always be positive and greater than 0, which positive, I know, that's redundant. Okay, so what would we do? Product minus reactant. So 2 moles of H2O gas times the 189 minus 2 moles of H2 All right. Sig figs are always sticky with these. So of course our coefficients would not limit us. Okay, so we should get 378 joule per Kelvin. Technically the moles cancel, yeah. Minus 262 plus the 205 and 467. And I know, Jackson, you are just thinking to yourself, see, I know what I'm talking about. Negative 89 joule per Kelvin. Easy. We just need to be super careful that we're applying our coefficients properly and that we're careful about our units and of course, careful about sig fig and absolutely that we're doing product minus reactant. Good? Definitely good. Definitely good. Definitely good. All right. So this was from 2019, one part of the question. I will read it aloud because I understand this. Hard to see on the screen. Using particle level reasoning, explain why the change in entropy of the solution, so we're making a solution, is positive for the dissolution of urea in water. Dissolution, remember, is a word we can use for dissolving urea in water. We do not have to know what urea is. We are dissolving urea in water. The question is, why is that process going to be positive? From the name, do we know if it's ionic or covalent? No, we really don't. Urea is a common name, but if it were ionic, I betcha they'd give us the ionic. But even if we don't know that, we know if it is dissolving and it's dissolving, so is it starting in the solid state? Well, no matter what, it's pure urea, and then it's going to be solvated and surrounded by water molecules. So what are our, not that there's magic terms, but there's correct terms. So why are we increasing entropy in that process? Too easy of a question, Mrs. Gerhardt. So what magical correct term did Anna use? Dispersion. I love positional probability. So during the solvation process, or when urea dissolves, it increases dispersion because, transitioning or, starting with pure urea, transitioning to solvated, mobile solvent or solute, sorry. I probably put surrounded by solvent. But the important thing is, of course, increasing dispersion. Okay, so can I share the rubric with you? And whenever we look at the rubric, they are just sharing maybe one possible thing that was accepted. I corrected this question, and I can tell you that we accepted more things. So urea molecules in solution have a greater number of possible arrangements. This increases, it corresponds with a positive delta S. Also greater dispersion, greater amount of microstates, greater positional probability. So I promise this correct terminology is what we want to be using. Okay, so enthalpy, we have different ways of getting it, and we know that thermodynamically, we want to be exothermic. Well, entropy, we know thermodynamically, we want to be positive, and one way we can get it is by applying the absolute entropies of product minus the absolute entropy of reactant. But there's one final decision maker, and that is the granddaddy thermodynamic equation. Gibbs free energy. Okay, so if we want to go into our packet, okay, so we're on page 17. Okay. So Gibbs free energy was experimentally derived, and your textbook does a beautiful job showing you where this equation comes from. We won't have to derive it, we just have to apply it. All right. Usually we're looking at the process. So where do we end up versus where do we start? So this is commonly the form that we employ, not just a here and now. This is really the form. This is probably the most used thermodynamic equation. All right. This gives us the final answer if we're thermodynamically favored or not. So, Luke, as far as enthalpy goes, what sign do we want on the change of enthalpy to be thermodynamically favored? Negative. We want this to be negative. And we want our entropy to be positive. T for this equation must be in Kelvin. Okay, we're taking our temperature times our entropies. Our entropies are given per Kelvin mole, per mole Kelvin, and we'll never have a negative Kelvin. So this second term, as far as the temperature won't make it ever a negative, and a negative. So if ideally we want entropy to be thermodynamically favored to be positive and enthalpy to be negative, then what sign will delta G have when both things are cooperating so it is overall thermodynamically favored? If this is negative and I am subtracting, T won't make it positive. I want that. So this will be a negative term. So go ahead, ma'am. Yeah, a big old negative. So negative delta G says it is thermodynamically favored. End of story. Go home, So we can't come back and say, well, what if, or how about this? Nope, done. Yeah, so that means it is spontaneous. Yes, Maya. Yes, you certainly can. So if it is positive, you have some work to do. It is not thermodynamically favored or non-spontaneous. Okay. Why do we call it free energy? So it's a little bit of a stretch, but this can be our interpretation. Totally fine. Why do we call it free energy? Okay. When delta G is negative, the process does that much work for us. That's the work that's free for us to tap into. Where if it's positive, that's the work we have to do, either by inserting a certain amount of heat or something else. Okay, so that can be like our interpretation. If it's negative, that's how much work we'll get out of the reaction, where this, that's how much work we have to do. All right. Can we look at page 18? Okay, but it is not so cut and dry. Don't you know? Not hard, but not so cut and dry. Okay, so we know, James, that for it to be thermodynamically favored as far as enthalpy, what sign do we want? You got it, you got it, you got it. And we know we want to increase entropy, but what if we don't? What if we're decreasing entropy? Well, I'm subtracting a negative, and so this is going to be a positive term. Well, what does that mean about spontaneity? Well, that is where temperature can be. That was fun. Again, I didn't fall. I'm so sorry. Or like, I don't know, hit my head or something that I'm sure you would enjoy viewing. So sorry, just clumsy as always. Very sorry, very sorry. Okay, so when they're both not the thermodynamic favorable way, temperature can make a difference. Temperature can make a difference. So if we want things to have a negative delta G, if that's what we want, then we want to run this at a low temperature. So at a low temperature, hopefully this will not be greater than that. Yeah. Okay, so when can temperature play a role? Do we see? It's when the terms are not in agreement, if you will, in making delta G negative. So if I'm not mistaken, no, false. Check something very quickly. Yes, okay, so. All right. So what if we had this equation presented to us? Okay, I'm just going to recreate that table. And so when our delta H, positive, positive, negative, negative, and then our delta S naught, positive, negative, positive, negative. When will delta G naught be negative? Okay. Okay, so Zach, first thing I'm going to look at is where are they both cooperating where temperature will not play a role. Okay, so if I am positive and positive, T will always be positive, positive and positive, will that always result in a certain sign on delta G? Shoot. So it'll always be positive. So will that be thermodynamically favored or not? If you do. Yep. So it is not thermodynamically favored. And this would be at all temperatures. Temperature cannot make a difference. Is that okay, Jackson? Yeah? So are we right? No. Zach, I just thought a second ago, like, is this too simple for my students to think through? I know you're awake by this time of day. Okay. We want a negative sign on this. That is what we're striving for. So if we're starting out, that's positive, and this is positive. I have a positive minus a positive. So, oh, I am so sorry. Thank you so much. Okay. So, endothermic. So this is not the way we want it. We don't want it to be endo. That's contrary to being thermodynamically favored. But this is in our favor. We want to increase entropy. So if this is positive, but we're subtracting this, so this is going to end up being a negative value, we want it. So when we take the temperature times this, it is greater than this. Because when we're subtracting that, and this is positive, we'll get a negative. So do we want low temp or high temp? We want it to be thermodynamically favored. We would be thermodynamically favored at quote unquote high temp, right? And we may say, well, how high? Well, we would understand it would be a great enough value that would put this to be greater than that. We want it just enough so it's greater, not equal to. Okay, make sense? All right, so what is our other? That's what we want. It's always going to work. If we are negative, it's exothermic, yay, and we're increasing entropy. Those are both in our favor, no matter what the temperature is. So it is thermodynamically favored at all temps. So that would be ideal. Okay. Where is it non-ideal no matter what temperature when both are in the direction that's not? Okay, that's where we'll start tomorrow. Okay, tomorrow we'll solve this equation. We'll look at how Gibbs is tied into equilibrium and start to practice. Practice tomorrow, practice Wednesday. We'll see how we feel about the content from there.